Good morning. Can you hear my voice?
Yes, sir, you're audible, sir.
Okay. Okay.
Yes, sir. Dr. Chirmay, sir, you're audible, sir.
Okay. So it's a good number of students, participants. As I
good.
can see, there are 232 participants.
Good morning to all the participants. We have Dr. Chirmaya sir with us. Today, sir is going to enlighten us related to electrical vehicle technology, categorization, and comprehensive insight. Before that one, I am introducing Dr. Chirmaya sir to our participants. Dr. Chirmaya sir has completed BE degree from Malnad College of Engineering, Hassan, Karnataka, and MTech in Power Electronics and Drives from NIT Warangal, and PhD in the area Electric Drives and Power Electronics from Indian Institute of Technology, Roorkee. And he completed postdoctoral research fellowship from Nanyang Technological University, Singapore. His areas of interest are multi-phase machines and drives, power electronics, renewable energy applications, electric and hybrid electric vehicles, smart grid. And SAR has very good publications related to this electric vehicle concept. Some of them are solar PV and grid-based isolated converter for plug-in EV. Then experimental analysis of various space vector pulse width modulation techniques for dual three-phase induction motor drive. Then a single stage integral charger for electric vehicles and plug-in electric vehicles incorporating induction motor drive. And a multifunctional integrated onboard battery charger for plug-in EV. And one more, a compact integrated charger with disturbance reduced induction motor drive for plug-in electric vehicles, and many more are there. I have quoted very few. And SAR has good expertise in MATLAB, Simulink, RT-Lab, LabVIEW, OpenDSS, LaTeX, control hardware in loop, and power hardware in loop testing. And SAR has interested in the areas multi-phase machines and drives, power electronics, renewable energy applications, electric and hybrid electric vehicles, smart grid. And he is an experienced researcher, skilled in modeling analysis and testing of power electronics and industrial drives. Welcome, Dr. Chirmaya sir, for today's section. Dear participants, we are very fortunate to have Dr. Chirmaya sir with us. Sir is going to deliver lecture on the topic electric vehicle technology, categorization, and comprehensive insight. Welcome, Dr. Chirmaya sir. Please start your lecture, sir.
Thank you, Professor, for the detailed introduction. As I can see, there are huge number of participants, around 250. It's a good number. As we give a lot of online lectures, we never see this many participants in one online lecture. So it's interesting for us to talk with all of you. So it will be an interactive session. So you can interact me in between. So let me just share my screen. My screen is visible, right?
Yes, sir. Screen is visible, sir. Dr. Chirmaya sir, screen is visible, sir.
Okay, yeah, fine. Okay, so as Professor Sridhar has already introduced, so I will be talking about electrical vehicle technology. Okay, so what do we mean by EV technology? So this period, whatever the period from last one decade to the next decade, we call this as a golden period for the researchers in electrical engineering, for the researchers and scientists in electrical engineering, because there has been a abundant development in IC engine in the last 50 to 60 years. Now the EV technology, electrical vehicle technology, is maturing day by day. As we know, still we do not have an EV which can compete with an IC engine. Okay, so why is that? Basically the initial cost and the range of the electric vehicle. So this has led to the researchers to work in charging technology, propulsion, and regenerative braking, all these areas of the electric vehicle. So in this lecture, I will basically give you an introduction to the EV charging technology. What are the types of chargers we can use in EVs? What are the types of chargers are being used, and how we can work on it? Okay, so this will not be a lecture like this will not be a lecture which you are not heard of, something like that. In this lecture, I will be basically showing you the experiments we did in the laboratory, the chargers we developed by ourselves, and what are the research you can take part in, or you can do it if you want to do your PhD, or if you want to work in electrical electric vehicles. Okay, so before starting, if there is any way, I would like to know if there are any researchers who are trying to figure out their field as of now, like first year PhD students or assistant professors who are looking for their PhDs. Is there any way I can know that one in the chat box or something? Hmm? So, convener, Professor Sridhar, is there any way I can know that, like, if there are any PhD scholars in the first year, or anyone who is figuring out their research area as of now? So you can let me know as we go on with the lecture. Okay. So this will be the table of contents for today's lecture. So different types of chargers, EV chargers, and how do we develop an EV charger? What are the criteria to develop an EV charger? And then there are different types of electric vehicles, like how can we improve the range of an electric vehicle by including multiple energy storage elements, like we use battery. Along with battery, what else can we use? Can we use solar along with battery, all these things. So in this one, I am basically categorizing the electric vehicle based on its chargers. Okay, that is what the lecture means. We are basically categorizing the electric vehicles based on the charger types. Okay, so coming to the introduction. Coming to the introduction. So, as I have already told you, plug-in electric vehicles and hybrid electric vehicles are being considered as the mainstream transportation in the future of the mainstream transportation. That means all the countries, most of the countries are trying to phase out their IC engines. So one reason, as we already know, this is in order to reduce the emission. Okay, as we know, Delhi, they made odd even, and they are making a lot of things in order to reduce the air pollution, in order to reduce the particles in the air, so that the people, the common people in that region can breathe good air. Okay, so how can we do this with EVs? Like, as the electric vehicles increases, the emission of the gases will reduce. Okay, that is one reason why the countries are pushing for electric vehicle. The second reason is for the stability of the nation. Like, if we are dependent on the oil, as much as we are dependent on the oil, or any country is dependent on oil, it should be on another nation. Like for now, as you know, the dollar to rupee is increasing day by day. Why is that? Because US dollar is the only way in which we can buy the oil. Okay, so any country can buy the oil with the US dollar itself. So it's a threat to the national security, not only India's, all the countries. So if we switch from oil dependency to non-oil dependency, all the transportation sector switches from that one. So it also increases the security of the nation. So for these two reasons, one is for environmental concern, the other one is security concern, all the countries are pushing for electric vehicles. Okay. So batteries, the chargers in electric vehicles can be classified into two types. Okay, can be classified into two types. They are off-board chargers and on-board chargers. Okay, so in this diagram, we can see the off-board charger and an on-board charger. What do you mean by off-board charger? As you can see here, this one, can you see my cursor? Can you see my cursor in the screen? Can anybody reply? Hello?
Yes, sir. Yes, sir. We can see the cursor, sir.
Okay. So as you can see here, so in this one, this is an off-board charger. What do you mean by off-board charger? charging station will be situated, or charging converter will be situated in a charging station outside the electric vehicle. Okay, so then we have onboard chargers. There are two types of onboard chargers: level 1 onboard charger and level 2 onboard charger. What do you mean by level 1 onboard charger? Level 1 onboard charger is a charger. Universally, you can charge your electric vehicle from anywhere. Okay, it won't charge your electric vehicle fastly, but even if in your office, in your house, you can connect it to the available socket and it will charge your electric vehicle. So this is level 1 onboard charger. Level 2 onboard charger can be a public or a private charger which can charge your electric vehicle rapidly. Okay, so the difference between these two is high ampere is available in the level 2, and it's the universal socket in which in your home it won't charge it that fast. So these two types of chargers are known as onboard chargers. So for this chargers, we need to have an onboard battery converter, which can convert AC to DC and power factor correction and DC to DC. Okay, DC to DC, the required voltage level for the DC bus of the electric vehicle needs to be converted inside the electric vehicle itself. Okay, whatever the AC output we are connecting, this conversion needs to happen inside the electric vehicle. This type of operation we basically call it as onboard EV charger. The converter is inside the converter, which converts from AC to DC, exists inside the electric vehicle. The level 3 offboard charger, this one can directly feed the DC bus. This converter is not required for this type of offboard charger. Okay, so there are few electric vehicles which only come with offboard chargers. You cannot charge them from your home or any AC power supply available. Okay, but those type of electric vehicle, you cannot sell them in India. Why? We do not have the required infrastructure for this offboard chargers. Okay, you do not have the offboard chargers every 50 kilometers or 100 kilometers as it is required. Okay, but wherever this infrastructure is there, for example, European countries, the country itself, Dutch country itself is a very small, like Netherlands. They have abundant charging stations wherever you go, and the country itself is so small, and they can install the charging stations. So in order to remove the additional cost, they do not have onboard chargers on the small electric cars. The electric cars are very small and they do not have onboard chargers. But that cannot be used for Indian technology. Whatever the cars you see in India, EV cars, for example, you can see Tata Nexon or any other car, it has an onboard charger from which you can charge it from your universal power supply. Okay, the socket. So as the country is large and it's developing, any country, even US, most of the electric vehicles in US has onboard chargers. Why is that? Even though it's a developed country, they do not have the charging stations as required, 100-kilometer range or 50 kilometers range, because the country is very huge. Okay, so if they till now they do not have this infrastructure. So most of the vehicles in US, they have this onboard chargers. So with the onboard charger situated in the electric vehicle, we can charge it from any universal power supply or from a offboard charger which can charge it very fast from a DC power supply. This will basically bypass this converter. Okay, so what research is going on to develop onboard charger as required, like the best onboard charger? How can we work on this one? Okay, what can be done to make it more efficient, compact? See, first thing is, let me go, the types of onboard chargers. Okay, onboard chargers can be further classified into isolated and non-isolated charging systems. Okay, so what do you mean by isolated? In the isolated charger, battery is basically isolated with a transformer. If not transformer, with an inductor. In DC we do not have transformers. In DC we have high switching frequency inductors. Okay, for example, flyback converter. So it basically provides isolation from the source to the battery. Okay, so isolation requires transformers or inductors of bulky higher size. Okay, so we go for non-isolated converters. If you have a non-isolated converters, you have to provide the safety by using control. Okay, there should be a closed loop control which monitors the SOC of the battery, and if there is any mismatch between the supply and the battery SOC, immediately the charging will stop. Okay, so we go for that one because isolated converters are bulky in nature and non-isolated converters are compact and they can fit inside the electric vehicle. So if your charger itself is very heavy, how long you can think that electric vehicle can pass. Okay, for that reason we reduce the size of the charger. Okay, again, non-isolated onboard charger can be classified as conventional and integrated chargers. What do we mean by this one? What do we mean by conventional and integrated chargers? Okay, so an onboard charger basically has these many parts. Okay, EV basically has these many parts. Okay, not only charger, EV has these many parts. So first part is grid to from AC to DC conversion from grid, a rectification. Okay, rectification. Then there is a DC-DC conversion. Why do we have this DC-DC conversion? This DC-DC conversion, whenever we convert from grid to the DC, grid available AC to the DC, you won't get the required DC bus there. Okay, you won't get the required DC bus voltage there. We want some specific value of DC bus voltage. So that will be achieved by this converter. Either it can be isolated or non-isolated. It's just a DC to DC converter. This basically charges the battery. Okay, this basically charges the battery. And then from battery, we have a bidirectional DC to DC converter. The operation of this one is this, what it does is it discharges from the battery to the DC link of the inverter. Okay, DC link of the inverter, and this DC to AC converter is basically an inverter. It propels the electric motor connected to the EV. Okay, so this is basically conventional EV converters used in conventional electric vehicle previously. So the researchers are trying to make it compact, as much compact as possible, the conventional converters as much compact as possible. So what we did, we basically combined these two things. Okay, this converter and this converter, and we can obtain a single converter which does the AC to DC conversion and brings the DC bus voltage to the required level. Okay, so this charges the battery, and again we have a bidirectional converter, and again we have a inverter. So this type of converter is known as single stage converter. Why is it called a single stage converter? It here, as you can see, in order to charge the battery, the operation is taking place in two stages. Okay, one AC to DC converter, then again one DC to DC converter in order to reduce or increase the DC bus voltage. So this two operations are being combined in one stage. So this is basically known as single stage charger. Okay, so first one is conventional, the second one is single stage. So is it the only way to reduce the number of components or minimize this one? No, we can also decrease this size. We can either combine any of these two converters in this single stage converter and go for integrated converters. Okay, they are known as integrated converters. So these are the terminologies provided by the scientists and the researchers working in EV area. So it doesn't mean that you have to go with the same terminologies. These are for our understanding. Okay, if you start reading papers in EV chargers, you will see these terminologies. What do you mean by single stage chargers? What do you mean by conventional chargers? All these things are terminologies provided by the researchers. Okay, so you can say, okay, this is a single stage charger you are saying, but as I can see, there are three stages here. Why is it single stage charger? So that kind of confusion can arise. It's common, but this single stage only refers to the conversion from the grid to the battery. So that occurs in a single stage. Therefore, we call it as a single stage charger. So what are the different types of single stage chargers? We basically have boost PFC converter. We have inverting boost PFC converter. We have SEPIC. We have Chuk PFC converter. So when anybody works on a charger, there are different criteria to compare the converters, compare the developed converters which can be used for EVs. Okay, what can we do? First of all, we can compare the switches, diodes, inductors, and capacitors. As you know, higher the number of switches, diodes, inductors, and capacitors, bulkier the size of the converter. So if you have a converter very bulky, then the range of the electric vehicle by itself will reduce. That we do not want that one. Okay, so we want a converter with reduced number of components. We want a converter which can. We basically want a converter which can. We want a converter which can do the required operation with the minimum number of components, and we also want a converter which can increase or reduce the voltage levels as per our requirement. What do you mean by this one? This I will explain in the later. This one. Okay. So what do you mean by onboard integrated charges? What do you mean by onboard integrated charges? As you can see here, size, weight, and cost of the charges can be reduced by integrating the converter stages. So we are basically integrating the converter stages. Okay. How are we integrating the converter stages? You saw the single stage converter here. Just hold on a moment. I hear some disturbance here. Let me just try. I can press them to stop. Okay. So onboard integrated charges. So integration means combining two things to make it one. Okay. So as I told you in the previous lecture, the previous slide, this AC to DC converter, the bidirectional DC to DC converter, and we have a DC to AC converter. So there are basically three converters now. Even after reducing the converter numbers, we basically have three converters in an electric vehicle. Okay. Can we integrate any of these two converters to make a single converter? Okay, so reduce the number of components required for reduce the number of components, size of the charger, and the range of the electric vehicle. So all these things can occur if we reduce the number of conversion stages. So that type of converters are known as integrated converters. So integrated converters, as you can see here, integrated converters can be of two types. Okay, so again, these classifications are done by researchers and scientists for the sake of understanding. Okay, so if you go for any papers, most of the papers follow this type of criteria, but it doesn't mean the integrated charger type 1 should be this one or integrated charger type 2 should be this one. It can be vice versa also. Okay, so what do you mean by integrated charger 1? In this type of integrated converter, we combine this AC to DC converter. We basically combine this AC to DC converter with the DC to DC bidirectional converter. We combine these two converters. In order to make a one integrated converter. So that type of integrated converter is basically called as integrated charger type 1. Okay. So what else can we do in the next integrated converter type 2? In this type of converter, what can be done is this three-phase inverter. This three-phase inverter is combined with the AC to DC converter stage. This three-phase inverter, what we call it as DC to DC converter, this is combined with the first stage in order to make integrated charger type 2. Okay, so I hope this is clear. Okay, so first we came from conventional chargers. Conventional chargers basically use these many converting stages. Then we came for single stage conversion. In single stage conversion, there was only one converter was capable of converting AC to DC and charging the battery. Then we also wanted to decrease the number of components, make it as compact as possible. What we did, we basically combined two different operating converters in an electric vehicle in order to make one integrated converter. So let us see what are the types of integrated converters that can be developed, how to verify that integrated converter, and how can we implement that converter for an EV. Okay, so while developing an integrated charger type 1, that means a converter which can use AC to DC bidirectional converter and a AC to DC converter and DC to DC bidirectional converter combined with a one converter, this type of integrated converter. How can we develop this type of integrated converter, and what are the criteria to develop this type of converter? Okay, requirement. So first, this should have power factor correction in plug-in charging mode. Okay, what do you mean by power factor correction? So can organizers, can they interact? Can the participants interact in this one?
Yes,
Is
sir,
it
they can
possible?
interact, sir. Yes, sir. Yes, sir.
Okay. Okay. So can anybody let me know what do you mean by power factor correction and why do we require this one? Anybody? So I've written power factor correction in plug-in charging mode. What do you mean by power factor correction and why do we require this one? Can anybody let me know? I don't know how many are you from electrical background, how many of you know power electronics or power systems, but still.
Most of them are from interdisciplinary, sir. Most of them are from electrical and sir, electrical and mechanical.
Okay. They can unmute their mics if they want to, right?
Yes, sir.
Okay. So can anybody let me know what do you mean by power factor correction? Or any idea in this regard? See, I just don't want to speak so much that you won't understand anything. There should be something. If I am speaking for 1 hour, 5-minute content you should understand at least the 5-minute content. That is the point. I mean, if it was an online lecture, it would have been easier for to offline lecture. It would have been easier for to interact. But in an online lecture, it's actually difficult. But still, so okay. So power factor correction. So when we charge from the grid, when we charge anything from the grid, we don't want to take reactive power from the grid. Okay, we only want to take real power. What happens when we take reactive power from the grid? The power factor basically decreases. What happens when power factor decreases? The voltage regulation reduces. The whatever the output voltage at the load side, it won't be the output voltage provided by the grid. Okay. So there are multiple drawbacks when power factor basically reduces. Okay, so we want to in plug-in charging mode, when the converter is charging the battery, we want that operation to be in unity power factor. What do you mean by unity power factor? We are only taking real power from the grid. Okay, then what do we want while developing an integrated charger? What do we want? We want buck boost operation in charging the battery. We want buck or boost. Basically, we want boost. Okay, because our charger will be of this by integrated charger. Sorry, basically we want buck because the battery voltage will be lower. Okay, still we must keep buck boost operation because we don't know what type of power supply will be available to us. Okay, so if we have a buck boost operation, what do we mean by buck boost operation? At the output side, at the battery side, the converter can reduce or increase the voltage based on requirement. Okay, so if we have buck boost operation in plug-in charging, we can connect it to any universal power supply available. Okay, ranging from 100 to 260 volt. You don't want to check the voltage rating and connect it then. So like your charger, okay, it can be connected to any universal power supply, mobile charger. But here we also need it to be connected to higher ampere voltage power supply. So we need buck boost operation. Okay, so we need bidirectional operation. Why do we need bidirectional operation? The regenerative power from the drive should be transferred back to the battery. Okay. Therefore, we need bidirectional operation. We need buck boost operation in propulsion and regenerative braking. This is for utilization of the battery SOC even if the SOC is low. If the battery SOC is high, we might require buck operation. If the battery SOC is low, we might require boost operation. So if we have buck boost operation in propulsion and regenerative braking, it's more efficient. So what we are trying to do is there are basically 3 stages. Before going further, there are basically 3 stages: plug-in charging, propulsion, and regenerative braking. What do you mean by plug-in charging? In plug-in charging, the electric vehicle is basically connected to the grid and the battery is being charged from the grid. Okay. In propulsion, battery is discharging the power to the drive. Okay, battery is discharging the power to the drive in order to propel the vehicle. Okay, in regenerative braking basically occurs when there is a slope or when we apply the brake and the machine can supply energy back to the load. Okay, or you can, in simplest way to think of it is, the vehicle is moving but the battery is not supplying the energy. It might be case of a slope, it might be downhill, all these things. It can supply regenerative power back to the battery. Okay, these are the 3 modes of operation in an electric vehicle. So if we have the capability to decrease or increase that voltage in all 3 modes of operation, our converter is efficient. And apart from all that, we need the size to be compact and has reduced number of components. Okay, this is the requirement in order to develop an integrated charger. Okay, so let us see one integrated charger which can do all these functions developed by us. Okay, so this one is a bidirectional chip converter based integrated charger. So what it does, it has voltage stepping down, stepping up and stepping down capability in all vehicular modes. That means it can step up and step down the voltage in plug-in charging, propulsion and regenerative braking. It also has a output inductor L2. This output inductor L2 reduces the switching ripples in the current. Okay, and it has reduced number of components compared to other integrated converters. So that we have compared it, and I will show that to you. As you can see here, these are the different integrated chargers. Okay, first one is boost PFC based converter. So in plug-in mode, it only has step up. In propulsion mode, it has step up and step down. In regenerative braking mode, it has step up and step down. So these are the number of components used by this converter. So as you can see here, there are different converters which has different capabilities. There are different converters which basically have, so we can see this converter which is inverting buck boost converter, this type of a converter. It has buck boost in all three modes of operation. That means it can do the function whatever we are proposing, the same type of function, but it has higher number of components. As you can see, the proposed integrated converter can do all three. In all three modes, it can increase or decrease the voltage levels, and it has the minimum number of components, only 3 switches, 4 diodes and 2 inductors. So in this way, we can develop the chargers and compare it with the existing chargers. Okay, we can develop the converters and compare it with the existing chargers. Okay, so let me show you the different modes of operation of the this chuck based bidirectional converter. So the first one is plug-in charging. Actually, there is this stuck here. Yeah, plug-in charging. In plug-in charging, we are basically charging the battery. Okay, we are charging the battery. In the first stage, we are charging the inductor, and in the second stage, actually in this stage, the capacitor charges the battery. Okay, in this stage. Okay, and in the second stage, the inductor along with the capacitor charges the battery VB. This operation, this first stage of operation is known as plug-in charging. In this one, this will be connected to the grid. Okay, as you can see here, it also has a diode rectifier. Okay, this diode rectifier rectifies the AC voltage from the grid to the DC, and the converter, the chuck converter, basically decreases or increases the voltage based on the battery voltage and charges the battery in plug-in charging. Okay, in propulsion mode, this battery voltage is the battery charges the capacitor, DC link capacitor CHV. Okay, this DC link capacitor CHV will be connected to an inverter drive system. Okay, the inverter drive system propels the battery. In this one, it charges the inductor, and in the second stage, the inductor charges the capacitor. Okay, this D1 and D2. Okay, similar to a buck boost converter. Okay, so in the first stage, it charges the inductor, and in the second stage, the battery along with the inductor charges the DC link capacitor. And in the third one, which is regenerative braking, the regenerative power from the inverter drive is charged to given back to the battery. So it operates in all these three modes of operation. Like all these three modes, the converter can operate effectively in all these three modes, and these are the duty cycle. As you can see, the duty cycle, it can operate in buck and boost in all these three modes. Okay, so the control. Okay, so how do we control? As I told you, this is a non-isolated charger. There is no isolation between the battery and the grid. Okay, there is no isolation. So by using a efficient control, we should protect the battery from any disturbance in the grid. Okay, in plug-in charging mode, we basically give the power input. Okay, how much power the battery needs to be charged, and the switching signals are generated by using this power signal, actual battery voltage, grid voltage and battery voltage. Okay, the gating signals are generated for the converter. And in the propulsion and regenerative braking mode, as you can see here, this switch is controlled. And how will we know if the converter is operating in propulsion mode or regenerative braking mode? How will we know that? That will be known by the torque input to the signals. As you can see here, there is a T torque. Okay, if the torque is positive, that means the vehicle is operating in a propulsion mode. If the torque is negative, that means it's operating in a regenerative braking mode, because we always consider the speed to be positive. Okay, when we consider the speed to be positive, you know that power is equal to torque into speed, T omega. If the torque is negative, then the power is negative. That means the regenerative energy is being supplied back to the battery. Okay, this is the simple control. I have explained it here, but when we implement it, it will be a little bit more complicated in closed loop. Okay, so these are the results. Okay, simulation results obtained after verifying the converter. As you can see here, the first one in plug-in charging mode, I told the converter should be capable of charging the battery in power with unity power factor. How will you know it's charging with a unity power factor? As you can see here, the voltage and current, or the black one is the voltage, the blue one is the current. They are both in phase with each other. So this means current is in phase with the voltage. That means the converter is operating in unity power factor. Okay. And the battery voltage is constant. It has charged the battery voltage, and as you can see here, the capacitor ripple, we have limited the capacitor ripple and the battery current. Okay, that is done by the output capacitor and the inductor in the output end. Okay. So in propulsion mode, what is our criteria in propulsion mode? The DC bus voltage should be constant. Okay. For example, let's say the torque and speed of the drive is changing. There should not be any effect on the DC bus voltage. Okay. As you can see here, in the propulsion mode, the battery is starting to discharge the current. This means the drive is in the motor is basically moving ahead. Okay. So, but even with that, the battery voltage is constant and the DC link bus voltage is also constant. Even though there is some perturbance, the DC link voltage is constant in the propulsion mode. And during the regenerative braking mode, the DC bus voltage will vary and battery will start, but the current will be supplied to the battery. It depends on the duty cycle of the converter. The battery is being supplied the energy from the regenerative braking. Okay, so the same integrated converter results were experimentally verified. As you can see here, the current is in phase with the voltage. One is the capacitor ripple and the inductor ripple were within the specified limits. This is power factor operation is happening in the power factor correction is basically happening in the plug-in charging mode. And this is propulsion as whatever I showed you in the simulation, and this is basically regenerative braking. Okay. So with this one, we can observe that the developed integrated converter can be effectively used for onboard chargers in an electric vehicle. Okay. So with this one, battery can be charged from the universal power supply because it has buck and boost operation in both the in plug-in charging mode. Buck and boost both operations in plug-in charging mode. DC link voltage is maintained constant even when the battery SOC is low. In regenerative braking mode, the power is supplied back to the battery and it utilizes minimum number of components. So we can say that this integrated converter developed can work effectively for a small EV which requires onboard and offboard charging. So if we have an offboard charging, then what can we do? We can basically connect the offboard charger to here, okay, till this part. Okay, if we connect this part, if it can provide the exact DC bus voltage, we can basically bypass this part of the charger. Okay, so if you want to charge your EV from an offboard charger, you can directly connect it by bypassing the onboard converter in an electric vehicle. Okay, so this is about the integrated charger type 1. Okay, before going to the integrated charger type 2, I want to know if you have any doubts and did you get what I was trying to explain. So the point is, how can we work on the chargers required for the EV? Okay, so I'm not sure. So what the researchers do, we basically develop different types of chargers and either we patent it or we publish it. Okay, so if based on the requirements, any company or a manufacturer can utilize this technology for the charging time. And there are few problems with this one. The main problem is the whatever the charger we developed, it basically provides an inverting battery voltage. Okay, inverting battery voltage. So that means for the positive grid voltage, we are getting the negative battery voltage. So the output is inverted from the input. This basically affects the control. Okay, this basically affects the control, overall control of the charger. So in the next stage, we basically try to overcome that one, but the number of components got increased. So you can start your research, or you can, if you want to work, you can work in this area um, in order to develop a the charger cannot be all good. Okay, if there is some plus point, there will be some negative points. So but based on the application, whatever the exact application we are using for a EV, so all EVs are not different. For some EVs might require higher range, some EVs might not require higher range, but lower range is sufficient, but they should be cost efficient. That means you have to develop an EV within this range. Some EVs like Tesla, they might need not to be cost efficient, but they require higher range, they require higher efficiency. So from uh, based on the different types of EVs, you can develop the chargers for them. So before going to the integrated charger type 2, if you have any questions, you can ask. Any questions?
The participants, you can unmute your mics and you can chat with sir. So we have few questions in the chat box here.
Yeah, I am seeing the chat box, but there are no questions in the chat box actually.
Okay.
So is the topic clear to you? I don't know. There should be, or do you think it's a little bit higher end for those who don't know power electronics? I don't know. How were the topics in your previous lectures? So this basically targets the researchers in the field of EVs. So it would be very beneficial for them. There are no questions.
Good morning, sir.
Yeah.
Is it what is the basic criteria to choose the design the charger? Is that the efficiency or is that the voltage level and charging duration? Is that the basic criteria or some other technicalities behind
See,
that to choose the?
okay, it's a good question. As I told in the beginning, so when we are developing an integrated charger, these are the contents we should keep in our mind. Okay, integrated charger. Okay, so criteria is like this one. Okay, so if you can have full control. Okay, what do you mean by full control? Your charger should be capable of decreasing or increasing the voltage depending on the requirement. That means there are three modes of operation: plug-in charging, propulsion, and regenerative braking. If in all the three modes, if you have buck boost operation, then it's best. Okay, it's an universal charger. Any EV can use this one because it has buck boost operation in all the three modes. But you can basically design a charger. So if you go for buck boost operation in all the three modes, you have to give up on some things. Maybe you have to increase the number of components, or in this case, you are getting an inverted output voltage in the battery side. So what we can do is you go for the exact requirement of the manufacturer. For example, let's say we have they require a charger in order to charge from a universal power supply, which is basically 225 to 30 volts. And what's the battery voltage? So in that case, if the battery voltage is less than that of the rectified DC voltage, you only need buck in the plug-in charging, you won't need boost there. So you can basically save one additional requirement. Okay, so then if the battery voltage and the DC bus voltage of the drive is very much higher than the battery voltage, you won't need buck operation there. You can do it only with the boost operation, right? So either you can design a universal charger or you can go for the application oriented charger. For what exact application are we designing it? Okay, and you might also, so if the control is the simplest control they want to use, then you cannot use a non-isolated charger. In that case, you have to go for an isolation between the battery and the so in what cases they use simplest control? If the EV is of low cost, they do not want to spend the amount in the what do you say, the FPGA boards or the control unit of the car. In that case, you have to give them the isolation. Okay, if you give the isolation, then they need not to spend that much money in the control. They need not to provide the safety of the battery through control. It's simple. Okay, if you have provided isolation, the battery is isolated from the grid and it saves. Okay, but it will increase the size of the charger. If they are not worried about that, you don't have to worry about that. See, basically application oriented. You can design a converter for the application. For some application we might need isolation, for some application we might not need isolation, like that. Okay, I hope it answers your question.
Yes, sir.
Okay, so while doing research you can choose your application. Okay, you can check while you go for the different types of chargers. You have reviewed it, so you observed, what did you observe? So what we call it as finding a gap. Okay, you have to find a gap in the existing literatures. Okay, so you should not go ahead without finding a gap. Okay, why did we design this charger? Because we came to know all the existing chargers have higher number of components, so we did not bother about the inverted supply, inverted output. Okay, so but when somebody is looking at my this converter, they might think, okay, it's an inverted supply, the control technique will be complicated. The control is already complicated because there is no safety here. Okay, so what they think, they can try to design a charger with non-inverted output and an isolation, so the control is as simple as possible. So we are going for the gap. Okay, okay. So any other questions? So let's go for the integrated charger type 2. Okay, as I explained previously, either we can combine the AC to DC converter with the bidirectional converter, or we can combine the AC to DC converter with the inverter. Okay, AC to DC converter with the inverter. So how can we do that? How can we combine AC to DC converter with the inverter? As we know, inverter basically supplies the drive. Okay, inverter supplies the drive. You won't charge it from the inverter. Okay, you have already have this method of this switches in your drive, but you are not using it. Okay, so you can use this inverter in order to charge from the grid. Okay, how? This inverter is only utilized in propulsion and regenerative braking mode. You are not running the drive, you are not running the motor of the electric vehicle while it is standstill. Okay, but you will charge the electric vehicle only when it is standstill. Okay, so you understood. So we are not utilizing one part of the EV for two different modes. Okay, for propulsion it's basically propelling the drive, but in charging mode this is basically standstill. In this case, in the previous case, it also has an inverter. As you can see here, inverter motor drive. This is not being utilized at all during the plug-in charging. This is being not utilized at all. Okay, so can we utilize it to charge the battery of an electric vehicle? As we can. Thus, that type of converters are known as integrated converters type 2, in which the inverter and the drive are utilized to charge the battery. Okay, so as you can see here, I can hear some voice. So as you can see here, our motor is nothing but an RL circuit. It has resistance and inductance. So we can use the inductance of the motor to eliminate, similar to my first converter, which basically had an inductor to eliminate to control the current and voltage ripples. We can basically utilize the inductors in our drive in order to control that current ripples. Okay, but we know whenever there is a space shifted this one space shifted motor, you give a time shifted supply. Okay, whenever the windings are shifted in space, you give a supply power or voltage shifted in time. For example, we have a three-phase winding phase shifted by an angle of 120 degrees. If we give the 120 degree phase shifted supply to it, it basically produces a rotating magnetic field. Okay, that's the concept of induction motor. So if you charge the induction motor from the supply directly, it will produce the rotating magnetic field, right? So if there is a rotating magnetic field, you don't want the drive to rotate, the drive will start rotating instead of charging the battery. So one thing we must keep in mind is that the rotating MMF should not be produced. Okay, how can we avoid rotating production of rotating MMF? There are different technologies for this. You can use the series parallel switch. You can charge it from one winding. You can keep the another winding out of the picture. There are different technologies. The simplest one is you can use multi-phase machines. Okay, you can use multi-phase machines. If you use a three-phase machine, if you are giving supply from three-phase, there will be obviously rotating magnetic field. You have to use a mechanical switches to avoid that one, or you give a single phase supply to the three phase, also there might be a rotating magnetic field, not in order to rotate the rotor, but there will be an MMF. Okay, so you have to keep your rotor locked. Okay, they all are mechanical. You need mechanical substitutes for your charger. Okay, that is not preferable. In order to use any mechanical switches or mechanical rotor locking, these are not preferred. Nobody wants to do that. Okay, so for example, you say you want to put a lock to your engine, you bring a lock, you put it to your engine, then you charge it from the supply. Okay, will you do that? No, you don't want to do that, right? So you want the control to take care of those things. You don't, nobody wants to switch on a mechanical switch, or means okay, I did switched off this one connected to the charger. Nobody wants to. The designers of the EV doesn't want their customers to do that. So what can we do? We can use multi-phase machines. What do you mean by multi-phase machines? Multi-phase machines are the machines where the number of phases are higher than that of the three, more than three. It can be a 5-phase machine, 6-phase machine, 9-phase machine. As I have shown you, a simplest 5-phase machine. This is a 6-phase machine. A 6-phase machine can be asymmetrical or symmetrical based on the winding configuration. If the two 3-phase sets are phase shifted by an angle of 30 degrees, it's called as asymmetrical 6-phase machine. Or if all the windings are shifted by 60 degrees, it's basically known as symmetrical 6-phase machine. Okay. So how can we avoid rotating magnetic field or MMF developed in this one by using multi-phase machine? I have shown you some examples. As you can see here, we have a 6-phase machine here. So instead of what we have done, we have shorted the one set of windings and we have connected the neutral of other two sets, okay, to a single phase supply. This will never develop rotating magnetic field. This will use this just as an inductor, and the inverter is basically acting as a rectifier. So the first two legs are not being used. Only the next four legs are being used from a single phase supply. Okay, from a single phase supply. On the other hand, in this case, the middle parts of these windings are connected to the 3-phase supply. So there is no rotating magnetic field occurs in this case also. It will be just acting as a simple inductor. Okay, so by doing this we can avoid the rotating magnetic field. If you wanted to connect it to 3-phase star connection, you can connect from this split winding to the 3-phase supply. You can get high charging at high currents, and also your machine will not be rotating. Okay, so the other way is, we have shown a 6-phase grid here. This is for the sake of simplification of multi-phase machine. There is no 6-phase grid. Okay, there is no 5-phase grid. But what do we mean is, if a winding is connected to, for example, so as we know, in order to develop a rotating magnetic field or MMF, the winding should be phase shifted in space. The the voltage should be phase shifted in space. For example, if you are not giving the first A in 3-phase, it's not possible. Why is it not possible? All the 3 windings are phase shifted by an angle of 120 degrees. Okay, whatever you give, it will just change the rotation of the direction of the rotation direction. But in 6-phase, it's not like that. So if you give A winding to the C winding and in complicated manner, it won't even rotate. That advantage we can take in this one. So there are chargers which use this one, and these chargers can also be connected to a three-phase supply. That means fast charging can occur, okay, by using multi-phase machine. Not required even without multi-phase machine. With three-phase machines also we can use this type of integrated charger too. You just have to make sure that there is no rotating magnetic field produced, okay, and there should not be a need for the mechanical switches. Okay, so these are the two types of integrated chargers. Okay, then coming to the secondary storage element. What do you mean by secondary storage element or secondary source? Okay, in this type of an EV, in this type of an electric vehicle, so instead of one source as a grid, okay, what till now what we have discussed in these two integrated chargers is we are using only one type of grid, okay, one source which is a grid, okay, we are basically charging from the grid, and we are using one storage element which is basically a battery, okay. So we can either increase the number of storage elements, we can use battery along with supercapacitor, you can use battery along with flywheel, you can use battery along with something else, okay, which has the different charge discharge cycle when compared to the battery. For example, supercapacitor. Let's take it as supercapacitor as an example. So we are using a secondary storage element such as supercapacitor. What's a supercapacitor? Can anybody let me know what's a supercapacitor? Any idea? Anyone? Okay. A supercapacitor is a storage element, okay, which charges and discharges very fast. Okay. It doesn't have a charge discharge cycle similar to the battery. So we can use multi-port converters instead of one port. Okay, whatever we did, we basically used in this type of integrated charger three-port converter. We use three-port converter. What do you mean by three-port? We have one port as grid, the another port as battery, the third port as a load. Okay, we use three-port converters here. Instead of two, we use three. Okay, that's how we combined single stage converter into integrated converter. So can we increase that one? Yes, we can. We can use multi-port converters. Okay, in a multi-port converters, you can basically add a source. What source you can add? You can add a PV. Okay, or you can add a secondary storage element like supercapacitor. So what is a supercapacitor? Supercapacitor can provide the thrust required. Okay. It absorbs large instantaneous power during sudden demand such as acceleration or regenerative braking. It supplies or absorbs large instantaneous power. Okay, so if you draw that kind of power from the battery, you will do is you will basically, for example, for initial thrust, if you draw it from the supercapacitor, then if you use the battery for a longer duration, the range of your electric vehicle will improve. Okay, but if you draw the current, the initial thrust current from the battery, you will reduce the battery life and the range of the electric vehicle. That can be provided by a supercapacitor. Okay, that is 5 minutes. That is basically the operation of a supercapacitor. Okay, so you are increasing the range of an electric vehicle. Okay, then you can okay, first let's talk about supercapacitor. When we come for supercapacitor, there is another problem. Okay, this DC link, it will be of higher voltage levels. Okay, the DC link for the bidirectional DC to AC converter will be of higher voltage levels, around 300 volt, not less than 300 volt, maybe more than 300 volt. The voltage at the end of the supercapacitor is very low, 12 volt to 24 volt. So you need a step up converter, okay, which can increase this volt and reduce this voltage in order to charge and discharge this one. So we need to consider this aspect in mind. So conventional buck boost converters cannot do this one, not even chuck converter. We have to go for switched capacitor based converters. There are different switched capacitor based converter if you want to include the supercapacitor. The simplest one is series parallel converter. In these converters, you basically charge the capacitor in parallel and discharge it in series. Okay, so you can increase the gain as much as you require. This is the modules can be added as per our requirement. Okay, so if you're adding the supercapacitor, you should know these things also. Okay. Then the next thing is you can add the solar PV. It will be a secondary source. Okay, instead of a secondary load, this is also the converter developed by us. I'm not going for more detail. As you can see, this is an isolated converter. We have isolation in this one, the whatever I was talking here, and it has a solar PV, and it can be charged from the grid, and it also has a battery and the load connected here. So this type of converter, this is known as multi-port converters. So you can use either super capacitor. You can add the solar PV in your this one. Okay, these are the simple explanation of the categorization basically of the chargers for an electric vehicle. Thank you. If you have any questions, you can ask.
Participants, if you have any questions, please raise your hand. We can unmute you so that you can ask your questions to the resource person. You can please raise your hand. You can use the button, hand raise option. Or you can also post your questions in the chat box.
Yeah, you can also post your questions. I am looking at the chat box.
Hello, sir.
Yes.
Myself, Venkatram Reddy, sir.
Yeah.
So it was very interesting. And one important thing, sir, related to the super capacitor. I got some idea, but to make it whether it is correct or wrong, only I raised my hand, sir. The thing
Yeah,
is,
sure.
the importance of super capacitor at this drive is only at the time of starting itself, because at the time of starting it needs more power to propel the vehicle. So the super capacitor will give a super fast, fast discharge, so that will help to improve the battery capacity. For that reason only we go for that, or what's that exactly?
See, it need not be during starting. Any instance at which the high thrust is required. Okay. For example, let's say you want to increase the speed drastically. Okay, you are going at 30 kilometers per hour. You want to go for 80 kilometers per hour. You will pedal. You will press the accelerator. At that time also it needs high thrust. Okay. So it can provide high thrust or high discharge in a shorter duration, but it charge discharge. So what we call is different charge discharge cycles. Okay, so supercapacitor has a different charge discharge cycle compared to the battery. By combining these two different charge discharge cycle elements, we can increase the range of the battery. Okay, it need not be during starting, it can be during any instances, but there should be energy in the supercapacitor. And also during regenerative braking, if there is a sudden inrush in the regenerative power, battery cannot take it. Okay, that can be supplied to the supercapacitor.
Okay, at the time of braking, so the super capacitor will regenerative time, it will start charging the.
Regenerative braking, not braking. There is a difference
Okay,
between
yes, sir,
regenerative
regenerative
braking and
braking
braking.
mainly.
Regenerative braking, supercapacitor can be charged, so that again, if there is a requirement, we can use that energy.
Okay, sir. At least I have one more doubt, sir. So at the time of regenerative braking, if the supercapacitor is going to charge in a faster rate, then what about the battery, sir? Will it be ideal, or how does it get charging, sir?
It won't be charged. Okay, so
Okay,
that
okay.
again, see in regenerative braking, charging battery is difficult than charging a supercapacitor. Okay, if the supercapacitor is not charged at all, so we will go for charging the supercapacitor. It's easier for us. Okay,
Okay.
charging and discharging a capacitor is always easier than that of a storage element. So supercapacitor comes somewhere in between of a capacitor and a battery. Okay, so our regenerative energy is not lost. Okay, in order to
Yes.
charge the battery during regenerative braking, the complexity of the control is more.
So one
Whereas,
word we can say it's as a supplement power, sir. Supplement
yeah,
power for
supplement
the.
power. Yeah.
And what is the disadvantage, sir? This is my last question. What is the disadvantage, sir, because of the supercapacitor? Because of that DC link, some disadvantage is going to happen. I didn't get that point.
Disadvantage is like not disadvantage. The voltage output of the supercapacitor is very low. Okay, the current will be high, but the voltage is low, 24 volts, something in that range. DC
Okay,
link voltage will be very high, 300 volt. So you want to step up this 24 volt to 300 volt, almost 10 gain.
Yes,
More than
yes,
10
yes.
gain. That you cannot
Okay.
get with the conventional buck boost converters. For that,
Okay,
we
okay.
need to have switched capacitor based converters. Again, so this
Okay.
complex converter has to be integrated with this charger. That is the disadvantage.
Okay, sir. Got it, got it. Thank you so much, sir. Thank you.
Welcome.
Thank you, sir. So we have another participant, Mr. K. Srinivasa Chalapati. So you can unmute your mic and talk.
Yeah, sir. Good afternoon. Thank you, sir. Thank you for the session, and it's really interesting because it's a new thing for us because some of the things are not related to mechanics.
Yeah,
But sir,
actually,
I have one doubt.
Yeah.
In the EV, the solar power, this one panels.
Yeah.
What is their efficiency in this, sir, and why the efficiency is not being made much, or the research is very low, or that kind of thing even in India?
Efficiency of the solar is very less, around 40%. Okay, not more than
Yes,
that.
sir.
The maximum
Yes, sir.
efficiency which can be obtained is 50 to 52%. Okay, that too for that some thin film solar panels which are being used. These are all like material aspects of the solar PV. So cost constraints, I think that's it. So if you want to increase the efficiency way higher, then the cost will be increased much more exponentially. Maybe that is the reason, but this comes in a material aspect.
Still in India, we are not in a position to manufacture the solar panels.
Yes. Most of the solar panels are imported.
Imported, yes, sir.
That drawback is there.
What is the drawback, sir? Why we are not able to manufacture them?
I actually don't have idea about that one.
Okay.
It basically comes to the material aspect. Okay, we have some
Yeah, it is because
researchers
of the
working on
material.
that one.
Yes, sir.
Material science, it comes to that area. So what we assume is we have solar panel with us, and how can we utilize it? That's what we assume,
Sir,
and
this
we
is
go for it.
Ilam
But based
Puran
on the
from
Thank
efficiency
you,
of
sir.
the solar,
Bye.
you're welcome.
Good morning, sir.
Good morning.
This is Ilam Puran from Bye here. I have one question.
Sure.
Regarding the supercapacitor, may I know the materials used in the sense what is its actual dielectric material used for supercapacitor, which could quickly charge and release?
Even that again goes for the material side of the this one. Even I don't have idea about that one. Again, we have supercapacitors here. We have supercapacitor blocks. We buy it and we use it as just as a battery.
What is the capacity at least?
So we have around 10 stacks of supercapacitor. Okay.
ಫೈನ್ ಫೈನ್ ನಾನು ಏನು ಮಾಡಲ್ಲ ಜಸ್ಟ್ ನಾನು ಒಂದು ಪ್ರಿಂಟ್ ತಗೋಬೇಕು ತಗೊಂಡ್ಬಿಡ್ಬೇಕಾದ್ರೆ ವಾಪಸ್ ಕೊಡ್ತೀನಿ
Hello?
ಆಮೇಲೆ ನಾನು ಇದನ್ನ
Yeah, we actually have 4:4, 16 small supercapacitor stacks in one block. Okay, in one block for the hardware implementation. I think it's around it gives around 10 ampere, 24 volt, something like that.
Okay.
Yeah.
Ampere hour, sir?
Yeah, ampere hour.
10 ampere hour.
Not 10 ampere hour. I have to check it. Exact value of that one.
Thank you.
We'll let him. Yeah. Any other questions? Mostly not related to materials. I can see the most of the participants are from mechanical background here, right?
Sir, electrical engineering background also there, sir. Many participants also there. Nearly 60% are from electrical engineering background. 40% are related to mechanical engineering, sir.
Yes, I can see.
Sir, this is
Okay.
Yeah.
Sir, I have one doubt which is related to that heat dissipation. Since yesterday also I'm having a same question. How the heat management has been? How the heat management has been done in batteries while charging and discharging? Because nowadays we are looking to forward to the fast charging technologies.
Yes.
Yeah, we are facing a lot of issues. Even the bikes, a few bikes has been blasted out.
Yes.
That was
Yes.
the reported was given as due to overheating, the battery has been lost.
Yes.
What are the things recent research is going on which is related to that?
Okay, that we have considered actually. The problem with that, why is it happening? Okay, so you have battery stacks connected in series or parallel. Okay, depending on the output voltage and current, we have batteries connected in battery stacks. Small stacks, they will be connected in series or parallel. So what happens is, so you cannot, it's very difficult to measure the individual SOCs of those stacks. Okay, so while charging that, so we battery management. This is a pure problem with the battery management system, BMS. What we call it as BMS, whatever you use in the battery management system. So one stack might be charged for 60%, the other stack might be charged for 20%. The overall SOC will be around 40 to 30%. The individual stacks should be charged. For example, you might know this water pumping application. Okay, if you have 1 minute, just 1 second. So this is the problem with battery management. So what needs to be done is individual SOCs must be estimated, and it's like you have the overhead water tank. Okay, so you have multiple overhead water tanks. What happens is only after one water tank fills, the water will flow to the other water tank. It should not be the case. When one water tank is almost 50% of the capacity, water should flow to the next water tank. Again, these are the problems happening with the blast. Okay, when the SOC is more than 90%, they are cutting it off, but that should not be the case. When 40 to 50%, then extra cell should be charged. If the battery management system is perfectly designed, India, it's the major problem. None of the companies are basically designing the or going for battery management systems. All of them are imported, and they're basically changing the configuration. Let's say if the battery management system was developed for one set of configuration, they are utilizing it for completely different set. It is not capable to handle that now. They are not, as I told you, application oriented battery management system needs to be developed. That can solve this issue. We are actually working with a company called Inverted.
Yeah.
We are actually working with a company called Inverted. So they are,
Okay, sir.
yeah, we are working on the same thing actually now to develop a battery management system.
We are also looking towards to that. How can we rectify the issue which we are facing nowadays? Even though the mobile phones, they are using a lot of technology to cool the mobile batteries, which is so whether we can add those things in this.
No, that is a different
battery.
technology actually. In mobile, we don't have
that.
stacks of batteries. That is the problem with something else actually. Both are different problems. This is a different problem. This is a different problem. Yeah. So this is coming because of the stacks of batteries connected together. In mobile, we actually have one single battery. That's a different problem actually.
I'm just giving for example how the technology 18 watts to nowadays they are using a 120 watts fast charging in mobile phones.
Yeah.
The same thing will be replicated in EV vehicles.
No, I have explained you the fast charging, right? Like we can use that fast charging. It should be, the converter should be capable of handling that. And battery management should be capable of charging the battery. Converter, see, in this one, we have not explained the battery management system. We have just shown you the battery here. Only the battery is shown. So in between this and this converter, there will be a battery management system here. Okay. So that battery management needs to figure out the power coming from this grid and the regenerative braking, how to manage the series or parallel connected batteries and charge them individually. That is the different topic, and that's the case with the battery management system.
Yes, sir. Thank you, sir. Thank you, sir.
You're welcome. Actually, there is a construction going on here. I asked them to stop for 1 hour. They stopped it for 1 hour, then again they started. So there is that much disturbance here. Yeah. Any other questions?
Thank you very much, Dr. Chinamaya, sir.
Thank you for inviting.
For your experiences and research knowledge. related to electrical vehicle technologies. This section is very useful for all of us, sir.
Thank you.
And with your vast research experience on EVs, you have given a good presentation. And participants also very happy to receive the answers from you. Thank you very much, sir.
Thank you for inviting me. You can share my email ID with the participants. If they have
Yes.
any queries, if they want to ask anything, they can email me. Preferably.
Sure, sir. Sure, sir. Please share PPT also, sir, to me. Then I will share to all the participants.
Sure. I will email it to you. Okay.
Thank you very much, sir. Hope we will have fruitful interactions in future also.
Sure, sure.
Participants, thank you very much for participation. And Dr. Chinmaya sir also have given wonderful presentation on EV technologies with his vast experience and research knowledge. Very few persons are available across the globe related to these technologies, because still it is upcoming technology, still many challenges are there. Yesterday also, keynote speaker from Germany, he quoted what are the challenges related to EV development. And today, Dr. Chinmaya sir enlightened us related to the developments. And thank you very much, Dr. Chinmaya sir. Hope we'll have interactions in future also. Participants, tomorrow the section will start at 12 noon because speaker is from England. So due to the time adjustment, we are scheduling the program at 12 noon. That is already conveyed in the schedule. Please make a note of it and give the feedback. Link is posted in the chat box. Thank you very much to Dr. Chinmay sir and to the participants.
Spoiler ka mula di bana kung ano